So the next topic is about triple five timer. So it is one of the important circuit in the analog and digital world because this is the circuit which is used to generate clock signals in the earlier era of digital electronics. Okay, so this is one of an important circuit, and it's in IC form. Okay. So it is an triple five timer IC. Usually it is called a triple five timer IC. So this is the internals of the triple five timer. So if you look at this circuit, okay, so this is nothing but a comparators. These are comparators. So comparators are very useful for making this kind of circuit. It's also a comparator. Okay. So if you look these two comparators are as configured as earlier in the previous previous lecture. I mentioned this comparator configuration, window comparator configuration, is useful for in the application of timing circuit. That's why it is found in this circuit. Okay. So the the reference voltage is given by a resistor network. So this is a, three resistor network. Usually, then if you look at this one, so this is the resistor network. So if you look at this, so if V is the input voltage, then if all the resistor are of equal values, then the voltage at this point, okay, let it be 1 and this point be 2. Okay, so let's analyze what's the voltage at point 1. Okay, at point 1, if you look at, we have the resistors, we are measuring the voltage across this point and this point. Okay, with respect to the negative terminal. Okay, therefore according to the uh, voltage divider formula, we know that we have, if we have two resistors, right, we have two resistors like this, and if this is R1 and if this is R2, then if we want to know the voltage across R2, what we do, voltage across R2 equal to R2, right, R2 divided by R1 plus R2 into V in this input voltage. Similarly, if you look at this circuit, so instead of R2, we have one R and another R. Okay, therefore we have two R. Therefore, at point one, we have the output voltage. Okay, V1 equal to at point one equal to R plus R 2R, right? 2R divided by R1. This is R plus 2R, right? Therefore, we have 2R divided by 3R. Therefore, it is 2 by 3. Therefore, at the voltage at the point 1 is two-third of the input voltage. Okay. Similarly, if you look at the voltage at the point 2, so at point 2, we have the resistor R. Okay. Therefore, voltage at point 2 equal to R divided by, if you look, we have an R plus 2R. Okay, R plus 2R equal to R divided by 3R into V. Okay, so place R divided by 3R into V in, or the voltage at point 2 equal to 1 by 3, okay, of the input voltage. Therefore, similarly, if you look at this point here, it is 1 by 3V, okay, the voltage, and here it is 2 by 3V in, okay, V in or VCC, this one, this voltage. So this window comparator is the lower threshold voltage is 1 by 3 of this this voltage, the input voltage, and 2 by 3 of the, and the upper reference voltage is 2/3 of the input voltage. Okay, so it is fixed between these 2 points. Okay, so if you look at this graph, time versus input voltage. The input voltage, the lower threshold is at 1.1 by 3, and the higher threshold is at 2 by 3. Okay, so this is the window. So it has an comparator stage, and the comparator stage is whose reference voltage is given by a voltage divider stage. Okay, this voltage divider stage. And there is another stage called the logic stage. In this logic stage is nothing but the two outputs of this comparator is fed to an SR flip flop or SR latch. Okay, SR. Okay, so the SR output looks something like this. Okay, this is the truth table for the SR logic. So if S is 0, okay, if S is logic low and R is logic high, then if you look that the Q bar follows the logic of R, okay, or the Q follows the logic of S. Okay, so in order to switch on Q bar, we have to reset the pin. We have to high the value of R pin. Okay, or we can switch Q to 0 by setting the pin S0. Okay, so if you have to, you can remember this by just remembering that either one of these pair, either R Q bar or S Q. Okay, so if in order to make Q bar high, we have to make R high and S low. Okay, this condition should be satisfied. Okay, and if both R and S are high, then the Q bar and the Q follows the previous state. Okay, so it remains in the previous state, or it memorizes the previous state. Okay, and if we want to make a Q bar 0, then we have to set R 0. Okay, R 0, or as well as S1. Okay, this S should be set to 1 and the reset should be set to 0. Then we have Q bar equal to 0, and Q is nothing but the complement of Q bar. Okay, and if both the inputs are 0, then it follows the previous state. Then in that case, the Q bar will be high, low, and Q will be high. Okay, so these are the things you have to remember, and there are certain names for this comparator inputs. Okay, so the bottom comparator, which is an inverting comparator, because the input is given to the inverting terminal. This inverting comparator's input is called trigger input. Okay, and the top comparators which is an non-inverting comparator whose input is called threshold. Okay, there is another pin called control pin, but it is not necessary. I'll discuss about it in the later part. Okay, so if so this is the circuit. So there is also another stage called the discharge stage. Okay, in the discharge stage is an NPN transistor. It is connected in a common emitter configuration. Okay, so therefore whenever this base is low, okay, whenever this base is low, the discharge pin is disconnected from the ground. Whenever the base is high, okay, whenever the base is high, the discharge pin is connected to the ground. Okay, whenever the base is high, if the base is high, then this point is continued like this. Okay, when logic 1, okay, whenever the base is high. So we can discharge a circuit based on the output of q bar. Okay, if q bar is 1, we can, the discharge pin is connected to the ground. Okay, it is pulled down to the ground. So let me demonstrate the working of this circuit as an astable multivibrator. Okay, so the astable multivibrator states look something like a square wave output. Okay, the output looks like a square wave. Okay, so this is the on state. Okay, this is the on state, and this is the off state. Okay, off state. So an unstable multi-vibrator is nothing but a square wave generator whose on state width and off state width can be altered. So what it means? So we can either make the off state small and the on state large. Okay, okay, or else we can make the off state large and on state small, like this. Also we can make the equal on and off states. Okay, so we can modulate the pulse width. Okay, the width of the this pulse. Okay, using the external circuitries, we can shape the width of this square wave. Okay, such a oscillator is called a multi vibrator. Okay, so we can construct a multi-vibrator using triple five timer, and the configuration is called an astable. Okay, it is not stable either in the off state or in the on state. It switches between the on and off state. That's the way it produces the square wave. So that is why it is called an astable. Okay, astable multi-vibrator. Okay, for that circuit we need some external circuitries. Let me draw some of them. So this control pin is not necessary now, so we can remove it. So let me erase these things. Okay, we can remember the top pin is the discharge pin, and this is called the threshold pin, and this is the trigger pin. Okay, so this is a non-inverting, and this one is an inverting comparator. You just remember those things. Okay, so in order to make this as an stable configuration, we need another R and C pairs. Let me draw them. So we have a um resistor connected to this discharge pin. Okay, we have another resistor connected here, and this resistor is connected to a capacitor. Okay, and it is grounded. So this is the circuit. Let it be RA, RB, okay, and C. Okay, let me redraw it neatly. So this is the circuit. Usually RA is very much less than RB. Okay, so the typical values are RA is usually of 1K. Okay, whereas RB is about 100K. Okay, and let me write here. So this is 1 kilo ohm. Okay, this is 100 kilo ohm, and this is around 10 nanofarad. Okay, 10 nanofarad capacitor. So this is the circuit for an astable multivibrator. Stable multivibrator. So we constructed an astable multivibrator using 555 IC. Okay, using 555 timer. So this part is the 555 timer. Okay, this is the 555 timer part. And we have an external RC network. Okay, so in this way we can create this type of square waves. Okay, the condition should be, this condition should be met. Okay, for a stable multivibrator, RA should be very much less than RB. Okay, I'll tell you why this is essential. Okay, so this is the, if you remember, this is the discharge pin, this is the threshold. Okay, and this is the trigger pin. Okay, so let's examine how this output looks. Okay, how the output looks. So this reset is not important as of now. Okay, for this discussion. So when we switch on, here we have to put VCC. Okay, we can tie these two pins together. Okay. So initial, when before switching on, this non-inverting input and sorry, this inverting input and this non-inverting input have a state. So this input is below this voltage, this reference voltage. Therefore, it is logic high. Okay, and if this is, because this is an inverting input. Okay, so if something is below this pin, it will go to the highest saturation voltage. Okay, and similarly here this threshold is also below this 2.3, so it is tied to the ground. Okay, so initially we have an 1 and 0 state. Therefore the q, this r is linked to q bar. Okay, therefore if the state of this or of different, then the value of r is moved to q bar. Therefore this point is 0 and this point is 1. Okay, initially the output of the 555 timer is, let it be, this is the logic state. Okay, so this is high state, logic high, and let it be, this is the logic low state. Okay, initially the output of this 555 timer is somewhere here. Okay, it will be here. And when we switch on the circuit, when we set the VCC to, when we connect this VCC to the voltage, input voltage, then this capacitor starts to charge through this R network. Okay, RC network. Okay, so it starts to charge, and the capacitor starts to charge through R and RA and RB. Okay, so this, we know that the capacitor starts to charge in this fashion. Okay, so whenever the capacitor starts to charge, it will starts to charge something like this. Okay, So when the capacitor is charge is about this 1 by 3 level, let it this be, this point be 2 by 3 level. Okay. So let this be the 1 by 3 level. Okay, here. So 1 by 3 level, and this is somewhat 2 by 3 level. 2 by 3. So initially when the charge of the capacitor is low, okay, we have an logic I state. Okay, logic I state, and this logic I state remains logic I till the capacitor reaches 1 by 3 of the reference. Okay, so this capacitor starts to charge and the voltage starts to rise, and this voltage is compared by this and this comparator. Okay, initially this the voltage here is less than 1 by 3 of this input voltage. Therefore, this is logic high and this will be logic low. And when and at the moment when this point the voltage is higher than 1 by 3 of this reference voltage, this inverter goes to logic low. Okay, but since this comparator is the reference voltage is even below this 2 by 3, this will remain in the zero state. Okay, so the R and S now have a 0 and 0 input, therefore the state remains the same. Okay, Q bar will be low and Q will be high. Okay, when the capacitor's charge uh, crosses 1 by 3. Okay, and when the capacitor charge, this charge, okay, this charge, this voltage crosses this 2 by 3. When it crosses 2 by 3, then this pin becomes high, right? Okay, when it is higher than this reference voltage, this will become high. Therefore our we have a 0 and 1 state. When there is a difference, then the state of R is mimicked by Q bar. Okay, therefore we have a 1 here, and as a result, since Q bar is 1, this will become 0. Okay, therefore, when the capacitor reaches two-third, okay, this region, okay, this region, it will remain high here and here. Let me use some other color. So this is the point, and here also it will be high. Okay, and it will be high, and when it reaches two-third, okay, two-third level, the output starts to drop, okay, to logic low, because Q becomes 0. This is where the output is. This is the output waveform. So it becomes 0, and the capacitor, and since this pin becomes high, Q bar is high, therefore this transistor starts to discharge this current. Okay, this capacitor's charge through ground. Okay, this network, because this is now high, this transistor is switched on, therefore this point is connected to the ground. Okay, and the current starts to flow in this direction. As a result, the capacitor starts to discharge. Okay, so the capacitor starts to discharge, and when it reaches below 2 by 3, okay, when it reaches 2 by 3, when the discharge and this point, at this point the voltage becomes less than 2 by 3, this becomes 0. Okay, this becomes 0. Therefore, since these are of same state, this the output is latched, therefore it remains 1 here. Okay. Therefore the capacitor starts to discharge again, and when it reaches this 1 by 3 voltage, when it crosses 1 by 3 voltage, okay, the capacitor's voltage, this pin becomes, when it is below 1 by 3, this becomes 1. Okay, therefore we have a 0 and 1 state. Therefore, whenever we have a different state in the R and S, this Q bar takes the state of R. Therefore, this becomes 0. The transistor starts to disconnect. It is disconnected from this circuit. The transistor no more conducts. Therefore, the capacitor starts to charge again. Okay, it starts to charge again, and when it crosses, so we missed two states here. Whenever this becomes this remains, um, the capacitor will be in the low state, remains in the low state, till this point. Okay, till this point it will be in the low state till this point. And when this when the capacitor voltage is below 1 by 3, then uh, this states changes. As a result, the q bar becomes 0 and the q becomes 1. Okay, then it starts to rise again. Okay, rise again and remains in the high state till this voltage is above 3 by 2 by 3. Okay, above this 2 by 3 it will remains in the on state, and when it is sorry, below 2 by 3, and when it reaches 2 by 3 it switches off again. Okay, and this cycle continues, and we have a square wave pulse. Okay. So this is the logic. Okay, based on this voltage level, this the output of the comparator switches on and off, and this results. This affects the output of this SR latch. Okay, this SR latch. So charges take place the voltage come through from RA, RB, then only it can charge the C. Okay, so for charging, the voltage has to the current has to pass through two resistors, whereas for discharging, the capacitor discharges only through RB. Okay, the circuit is completed here. Okay, it discharges through RB. Okay, so for discharge is this direction. Okay, discharge direction, okay, through this direction. Okay, so the charge circuit time. Okay, the charging of the capacitor depends on the value of the time to charge. Okay, charge depends on RA as well as RB. Okay, both the resistors, whereas the time for discharge is proportional to RB only. Okay, because the capacitor discharge through RB itself. Okay, it doesn't need to go through RA. Okay, the circuit completes here itself. So usually it is the time for charging. Okay, the time for charging is equal to 0.6 0.693 times RA plus RB into C. Okay, this is the time constant. Whereas for discharging, time for discharging, okay, is equal to 0.693 times RB into C. Okay, so this 6.93 comes from the time constant factor. Okay, it's a time constant factor. You can look at for the tau. Okay, the calculation of tau on the net, and you can understand why this factor comes from. Okay, usually the time constant is defined as time constant of an RC circuit. Okay, if you look at this circuit, okay, this is R and C. Usually the time constant is defined as the time taken. Let me write in a new page. Time constant of an RC circuit is is defined as the time taken by the capacitor to reach 0.693 times the input voltage Vi. Okay, the input voltage. Okay, so this is how the time constant is defined. Okay, so the time constant is nothing but the time taken for this capacitor to reach a to reach a voltage of 69%. Okay, 69% of this input voltage. Okay, that's the definition of time constant. That's the way this for this value comes here. Okay, so this is the uh, time for the this one. Okay, for the logic high state, the time, the width. Okay, the logic high, and this is logic low. Okay, so this is the width, this is the t tc. Okay, tc for time for charging, and td is the time for discharge. Okay, time for discharge. So if you look this, we can alter the width by varying the value of Ra and Rb. Okay, so in order to get a symmetric charging and discharging width, we usually choose Ra very much less than Rb. In such a way, this Ra can be neglected. Therefore, both the charging time and discharging time are of same values. Okay, that's why I made this statement here. This Ra should be very much less than Rb. Okay, for symmetric waveform, for equal Ta and sorry Tc and Td. Okay, so this is how the astable multivibrator works. Okay, so with this, today's topic is that's it, and we can discuss about op-amp multivibrators in the following lectures. Okay, thank you.